P4, particles and antiparticles. In this diagram here, we've got some normal particles, so this represents an electron, a proton, a neutron. On the dark side, we have their antiparticles, so an anti-electron, also known as a positron, an anti-proton, and an anti-neutron. There are various ways of representing them, but that's quite a nice way, black and white. So, in 1928, Paul Dirac decided that for every particle there should be a corresponding antiparticle. And the properties that antiparticles have are, first of all, they have the same mass, but they have opposite charge. That's if they are charged. There are a couple of other properties that are swapped as well, but you don't need to know about those for A level. If you want to know more about that, then do a physics degree. Okay, and Dirac was right. We can make or cause to form antiparticles, particularly in particle accelerators, and we also see them in the atmosphere caused by cosmic rays. So first thing that can happen is annihilation. If an antiparticle meets a normal particle, a matching normal particle, then they will annihilate each other, and that just means that they'll cease to exist. And all their mass will be turned into energy. In this case, 2 photons, okay, which come out back to back. Another thing that can happen is the opposite of annihilation is pair production. So that's when a very energetic photon can actually, under some circumstances, cause 2 particles to form, one of which is a normal particle and the other is an antiparticle, a matching antiparticle. So let's take annihilation first. Matter is turning into energy. So we start off with something that has mass, that's what we define as matter, and it's going to turn into just energy. So we can actually calculate the energy that's matter. It's called the rest energy. So if we think about annihilation, let's consider an electron and a positron meeting and annihilating. So they've both got the same mass. So in here we've got the mass of an electron. E equals mc squared. That's Einstein's equation. And we've got to double it because we've got 2 particles. We've got the electron and the positron. And on this side it's going to turn into 2 photons. And each photon has energy equals hf. But there are 2 of them, so we've got the 2 as well. So that's the 2 photons on that side. Now, very conveniently, you don't have to usually use that equation because the rest energy of an electron is listed on the formula sheet in mega electron volts. So we have an electron plus a positron. They both have the same rest energy because they both have the same mass. So we're representing the rest energy of an electron by E0. Okay, and we've got one for the positron as well. And if we equate those two, so the matter turns into energy, we have the formula 2E0 becomes 2HF min. Now it's minimum frequency because we're assuming that the electron and the positron are just going to sort of drift together with no significant kinetic energy. So all the energy of the photon comes just from the rest energy, or the mass, of the electron and the positron. So obviously the 2's cancel out, and we have this formula. The rest energy of an electron or positron becomes the energy of a photon. Now usually the particles have kinetic energy as well, so if we start with the energy of the electron, we could represent that as kinetic energy plus rest energy. The positron may have some kinetic energy as well, so kinetic energy plus rest energy. And that becomes the energy of the 2 photons, HF plus HF. So if all the extra kinetic energy will add to the energy of the two photons, so they can end up with a higher frequency. Going back to pair production now. So this is energy turning into matter. We've only, in the diagram I've shown you, there's just one photon, so we've got HF min turns into the rest energy of the two particles, so an electron and positron are quite typical. Any extra energy appears as kinetic energy of the positron and the electron. Okay, so obviously there's a minimum amount of energy that will create an electron-positron pair, but if the photon has more energy than that, then the electron and positron will just get the extra kinetic energy. This is a bubble chamber photo, so you'll see some in class, or maybe you've already seen them. In this picture, there's a gamma ray has come in from off the screen, and it's split into two particles, and one's curled to the right and one to the left, and in a bubble chamber that shows that they've got opposite charge, because the bubble chamber has a magnetic field across it, and that makes charged particles deflect. So as you can see on the label, this one is an electron and this one is a positron, and they go in a spiral because they're losing energy as they make the trails in the bubble chamber. If you put more energy in, so if you have a more energetic photon, then three things could happen. You could get more pairs, so the same photon could produce several pairs of particles, or you could make a more massive pair. In other words, the particles you produce may be something with more mass than electrons and positrons, or the particles could just have more kinetic energy. And in the diagram here, there's another gamma photon has caused another electron-positron pair. They're both curling, just like the first one. The way you can tell that this pair has more energy is that they haven't curled up so much, so they must be going much faster.